made it. Last night I tried to do it with Eugene and Lilian until around 12:30 a.m. something.
How was it? Any difficulty?
Yes.
Yes. Which one? The queuing or the Markov?
I think for the Markov chains, after we take a look back at your recording, we some sort of get it.
Okay, that's good.
Okay. So yeah, and me and Lilian, we we tried to wake up early today to try to finish, not finish. Well, we tried to finish, but we haven't finished yet about the Surabaya bus feasibility study.
Okay.
I have some question about the values of you have interest rate and then reduce time and also load factor. How do you get those numbers, sir?
If you don't get the numbers, you just assume. Load factor,
Oh,
the meaning, you should understand the meaning. Then you can assume, right? So factors mean in one bus, how many, what is the percentage that it is full? Load factor 100 mean everybody, all the seats are full, right? So if 80%, then you set 0.8. In Surabaya bus, you check in one observation, how many seats are full?
so the capacity is 40, but most of the times like based on my like rough observations, yeah,
Yeah,
like when
that's
I'm on
fine.
the road, it's usually around maximum 10, 20 or 15.
10, so that's mean only 25%.
I think around that number, 0.25. Yeah.
So 25%. Very low load factor.
Oh, so the load factor is the capacity,
The actual average number of passengers per the capacity.
yeah, per full capacity, yeah.
Correct. So, but the capacity may include two, okay? Standing capacity and sitting capacity.
I see. But
So,
I think in Surabaya bus case, it is designed only for sitting, so it doesn't have any standing, like it doesn't have any.
okay, then it's 40. So if only 10, then it's 25%. Very low.
Yeah. So I think in feasibility, for feasibility study, it is not feasible. How can we make
Only
it?
10 mean the one who join are either for pleasure or for the sake of trying. It's really good. Then it's about 80% or above. Sometimes it will reach standing capacity, not just sitting capacity.
So even if it's like the load factor is 80%, it's still
not enough, right? So in this case, based on your observation, around 25%. So you include 25%.
okay. But the you said like the price of the bus is around 80,000 to 90,000 US dollar, right?
You can check.
Yeah, apparently I just checked like last week we thought that it's around 80 to 90,000, but after I checked, is it the chassis of the bus. The chassis of the bus is like it costs 1.6 billion rupiah.
That means how much in US dollar?
I think around
100,000.
1.6.
110, right? Around 110,000.
118,000.
Yeah, so 120,000. So the price that I put there, it was 2005. So it's like 10 years ago with inflation rate, say 3 to 5% per year. That I think is reasonable to get 120, right?
Okay. And the interest rate, we just assume as well. We make it the
You
same
can check if you put your money in the bank, how much is the interest rate? Roughly in Indonesia, it's around 5%.
I think the late yeah, I don't know. We must take average, yeah. Average of interest rate in Indonesia.
Yes. Usually around 5. So things that you don't know, you can assume, right? Based on your observation. And today, I would like to discuss about maximum entropy. This is where you can assume something based on certain principle. Where is entropy? Yeah. Okay. Okay, shall we start with the lecture, or should we wait for others?
I think we can
We can start, right? Darren is not here yet. Okay, let's start. I will share my screen. Okay, so this is not in the slide or there. So, but partly I will discuss the entropy here, which is, can you see my slide?
Yes, sir.
Okay, so entropy. So entropy, the concept of entropy was started in physics. Okay, in 1855, someone named Rudolf Clausius proposed this formula. Looks very complicated with circle integral. Right? It's about the state of variables in the heat, in thermodynamic heat. So if you have a machine, right? So how the machine will have a process in the heat. Now, entropy is a state variable whose change is defined as a reversible process at certain temperature, where the Q is the heat absorbed by the machine. So it's starting with physics or mechanical engineering. Okay. And in 1872, Boltzmann in Vienna formulated entropy using this formula. S is equal to K log W. So S is entropy. I think you learned this in physics in high school, isn't it? Boltzmann constant. Did you study about Boltzmann constant in high school?
I don't remember this.
You don't remember this, okay? I do remember, but anyway. So W here is the number of possible microstates, okay, compared to the macro state. So in the very beginning, entropy is practically about complex system. What is complex system? The relationship between micro states and the macro states. Okay, but of course, this is talking about ideal gas particle. It explains how the heat happens. Okay, because inside have atoms that hit each other in the ideal gas. So it explained that when you have a gas like something in the right, okay, in the normal temperature, as the time goes, it will become something in the left. So the gas will expand, right? So similarly, entropy or thermodynamic entropy is the one that explains time, actually, because in physics there is no real things called time. So entropy is the first and the only one probably explain about the time arrow. That time is irreversible. Okay, so if you have a brick, something like at the bottom, throwing like this, and then you toss the brick, okay, or kick up the truck, then it becomes disorder, right? So if you break a glass, okay, and you cannot make it back into the glass, okay, unless you put certain energy in it, right? So there is certain energy and order and disorder relationship, which is part of the entropy. So if you look at this, entropy is the delta entropy, the change of the entropy, equal to the heat divided by the temperature. Then Gibbs in 1878 proposed this formula. Okay, again, he uses Boltzmann constant, but look at the formula, is now using probability. Okay, so if you input the probability is equal to 1 over n, meaning uniform distribution, okay, it will come back to Boltzmann entropy. So this is the relationship between Gibbs entropy and Boltzmann entropy. Is now Gibbs entropy practically generalized Boltzmann entropy, isn't it? Okay. You remember earlier we have a Boltzmann entropy down there, S equal to K log W, right? So, and Gibbs entropy is P log P times K, the same K here. Okay, but if you use the P here, Pi, the probability of the microstate equal to 1 over n, n is the number of states, then it will come back to minus K log n, which is equal to K log W, isn't it? That means the two equations are actually the same if and only if the P equal to 1 over n. Do you understand what I'm talking? Give me a question if you don't.
Yes, sir.
Okay. So next, in 1948, Shannon proposed this. So he removed entirely the K Boltzmanns, okay, the constant of Boltzmann, and he used directly P I ln Pi. Okay. So Clark Shannon is the father of information science. So if you talk about information science or information technology, it's all come back to this book called Mathematical Theory of Communication. if you want, I can send you the book. I have the PDF of this book. So why we use Shannon entropy later on, okay? So basically Shannon entropy is the most general entropy. It is the only one or unique and consistent with the three axioms below, okay? First, S or S is the entropy, is a continuous function of Pi. P is the probability. Now, if all Pi probability are equal, then the quantity S is a monotonic increasing function of N. So in entropy increase by the number of states. And then most importantly is there is a called composition law. So if we group certain events, okay, the entropy will remain the same as a linear combination of the group entropy with the weight of the group probabilities. So I want to explain to you spatially so that you can understand entropy in spatial sense. Okay, so I have a rectangle. Okay, so A is only one rectangle. B, that the same rectangle I divide by 2. Okay. In C, again the right rectangle of B I divide by 2. Okay. In D, the top right rectangle of C I divide again by 3. So my question is, how do you distinguish A, B, and C in terms of information? Okay, so each of these rectangle A, B, C, D have a unit total area. So how do you distinguish the information that these rectangles are actually different from each other? So can we find certain indices to distinguish this rectangle that actually invariant? The invariance means don't change toward rotation and translation. Okay, so because the total area is the same, 1, right? So the scaling is not applicable to this problem. So when I talk about these 3 transformation, rotation, translation, scaling, okay, this talking about the rigid body transformation. If you have a handphone, it's a rigid body, right? So if you rotate, if you translate, move, translate, okay, it will not change. If I do scaling, so I make it closer to camera or farther away, okay, it's bigger to you, okay, but actually the same phone, the size of the phone does not change. So rigid body transformation, okay, meaning that the rotation, translation, scaling does not change the rigid body size. Okay, so in the first attempt, let's try to sum each part of this rectangle. All right, you know the total sum is also 1, right? So say A, total area is 1, B, have left part and right part. So left part is half, right part is half. If you sum, become 1. So you cannot make a difference between A and B. Okay, but at least we learn something here. A, actually B have certain part and that part can be measured as half. The same thing with C. C have certain part, the left part is half, the right part is 1/4, 1/4. So by first attempt, you fail to distinguish the information, but starting with certain attempt, then you start to see certain things that you want to do. It is, oh, you have certain information there actually. The size is actually half and 1/4 and so on. Okay? Can you see that? Numbers now. So
Yes.
in D, you see the small part of A is 1/12, right? So then, in that case, let's try if we multiply that part, okay? If we multiply that part, what will happen? Okay, in A is 1, and so 1 multiplied by itself, so 1, right? So in B, half multiplied by half is 1/4, right? And in C, what? Half multiplied by 1/4 multiplied by 1/4. So we get these numbers. Yeah? The same thing with D. Oh, now you see, I can start to distinguish, okay, with this M, index M here, with this multiplication of the part, okay, I can say that A is B and C and D are different, isn't it? And you see the numbers are not the same, right? So this index is successful. Okay? The sum is not useful, but the multiplication is useful. But there is a problem here. What is the problem? The last part, the T, the M is very small. Huh? So in that case, one way to solve very small numbers is to log them. Okay? To put it's nice index actually, okay? Between 0 and 1. Okay? Very small value in D, okay? It's difficult to see them clearly. So one way to solve this problem is to use logarithm. Okay? So, but if we take logarithm, okay, the numbers become negative. So in that case, it will be multiplied by -1. So then we have minus log n. So someone already proposed this, okay? His name is Hartley. So then this index is called Hartley information measure. Okay? So if we use Hartley information measure, remember the rectangle A, M is 1, so then I, the Hartley information is 0. So the information is 0. Rectangle D, M is 0.25. Okay, we use log 2, then information is 2. Rectangle C, information is 5. Rectangle D, information is 13.754. Until here, can you start to understand that we can measure information?
Yes.
Okay, easy, right? So if you have a part, okay, then you multiply all part and then you log them and take negative value, then you get what is called information. Okay. So look at the information here. A, information is 0. Okay. B, information is 2. C, information is 5. D, information is almost 14, right? Oh, why? Why the information in D is higher than A? And why B, rectangle B, has information 2 is higher than information 0? What do you think?
Because there's more part.
Is it because of the number of parts, or is it because there are certain complexity there?
Complexity.
Okay. So if everything is the same, right, that is kind of boring, dull, isn't it? Then the information is less. But if something called interesting, meaning the information is more complex. Okay, so you can start to measure information.
So the more the rectangle is separated into several parts, is means the information gets more interesting?
Not necessarily the number of parts. It's how you separate the part. So if you just divide into 3 equal size, then again the information is dull.
Okay.
Okay. So if practically if you have no surprise, okay, least surprise, that means information is less. If you have more surprise, that means information is higher. Easy.
Yes, correct.
Okay, correct, right? That's
So so in this one like A B C D. So in like let's say if there's possible in form E, like the rectangle E means like it gets divided again.
yeah, if you divide again, then it's higher information.
Okay.
Okay. Okay. Let's another way now. Let's use what we want, entropy, right? So when we say entropy, right now we don't use Gibbs entropy. We don't use Boltzmann entropy. We always use Shannon entropy. Okay. So what is entropy in this case? Entropy is a measure of average information. Okay. So in that case, again, you use log 2. So P, okay, Shannon entropy is P of the part A multiplied by the log of 1 over P. Okay, but log 1 over P is equal to PA, but minus, isn't it? So then you can see that formula. Okay. Here. Okay. So this part is the one that creates the minus. Okay. So of course the total sum of AI is 1. Right? Remember the total area of the rectangle is 1. So why I deliberately say the total area of the rectangle is 1, so that you can see that rectangle can also serve as probability. Okay. So when we compute using Shannon entropy, okay, rectangle A has only one area, so the probability is 1. So then the S, the Shannon entropy is 0, because log of 1 is 0. Right? Rectangle B has 2 areas, the same part, half. So then you put input into this formula here. Okay. Then the result is 1. Rectangle C have a small part of half, 1/4, and then you input it into the formula of entropy, and then you get 1.5. Okay. Rectangle D, remember, have area of 1/2, 1/4, and 1/12, 3 of them. Okay. Then you input them into this formula. Okay. Then you get entropy of 1.8. So again, entropy is somewhat similar to information, isn't it? Okay, but the numbers is nicer. Okay, why is it nicer? Because when you have equal probability, the entropy is always 1. Okay, when you have equal probability, the entropy is always 1. So is it true? Let's try with here, example. Okay. Oh, sorry. The entropy ratio is 1, not entropy. So I will. So what is entropy ratio? Entropy ratio is the index between 0 and 1, okay, which is entropy S divided by the maximum entropy. Of course, the maximum entropy will happen if the all probability equal, right? The uniform distribution. So uniform distribution is 1 over n, right? So then if you input this into the formula of entropy, we have maximum entropy is equal to this formula. Okay, then you put it inside here, then you can calculate. Okay. Okay. When is maximum entropy happen? When they are equal probability. Okay. So rectangle A has only one area. So P is 1. So T in here is entropy ratio. 0 over 0. Actually, is undefined, right? So, but by definition, we put it equal to 1. Huh? So rectangle B has 2 areas, 1/2, n is 2. Then you input it into that formula, then you get the entropy ratio of 1. C have entropy ratio of 75, and D have entropy ratio of 0.5. So when they are equal probability, then the entropy ratio become 1. So let's check there. Yeah? So here, this entropy ratio is actually undefined. Okay, so I put 0 here. Here, you see the probability is equal. So the entropy ratio is 1. Again, this one is the entropy ratio is 1. This is divided by equal probability. So again, entropy ratio is 1. The same thing here. Okay, I divide by 4. Then entropy ratio is again 1. Again here, equal probability, then entropy ratio is 1 again. Can you see? Entropy ratio represent certain efficiency, right? So entropy divided by maximum entropy. Okay, until here, what did you just learn?
About entropy.
Okay, entropy and entropy ratio and information, right? So
Yeah.
How to measure information?
yes, how to measure information. Okay, and entropy is actually measuring information also the same, right? Okay, in data science, decision tree, for example, I have a book about this. So to separate the tree, one of the technique is to use entropy. Okay. So until here, is there any question before I go to the next topic, maximum entropy?
I guess we can continue first.
We can continue first. Okay. So let's try. But before I wait this, look at in Moodle. Okay, there is a slide about maximum entropy, and I have also posted assignment for you for maximum entropy. Can you check? So We'll start with the whiteboard. Okay. Say you have a slot. Okay, so let's say you have 5 slots. Okay, let's have this slot will fill with a number, with several numbers. Right? So if I have here 3, I have here 4, I have 1 and 2. Okay, and then I have 5 here. What is the sum? What is the sum? And what is the average
Of the numbers.
of this number? 3 plus 4 is 7.
7, 8,
1
10,
is
15.
10, 15. Huh? The sum is 15. Yeah. So, and then what is the average?
3.
3.
3. Okay. Okay. So now I will erase this. Okay. I will erase the last number. Okay. Now I want you to guess. Okay. What is this last number? Something with question mark here in the green. Okay. What is this last number? If I know that the sum is 15.
So 15 minus all of the numbers.
Yes, how? Then how many? So 15 minus
10.
minus 5, minus 4, yeah. Minus
Yeah,
5.
minus 1, minus 2.
Then equal to
5.
5. Oh, you can get 5, right?
Yes.
Good. This is called degree of freedom. DF. In statistics, did you learn?
Oh,
Yeah.
yeah.
What is DF? What is degree of freedom?
I forgot.
Okay. Or you just learn, oh, I have a DF here, and then I use the table like that.
Yes, yes, but that's what I learned in statistics.
Yeah, but you don't understand the meaning of DF.
Not quite, not quite.
Not quite. Okay, I will explain to you. DF is, okay, the maximum number of empty slot here, like the one in green in the question mark. If you know the statistic, okay, how many slot that you can return back the value. So in this case, I know the statistic is 15, right? Which is the sum or the average, okay? When we say statistic, is sum, average, standard deviation, maximum, minimum, right? Those are statistics, okay? So now if I know the statistics, okay, and I have this kind of array, okay, and how many slots I can fill in, okay, that represents the degree of freedom. So in this case, df is equal 1, right? Because if I know the statistic with this 15, I can fill in with this, you just fill in a while ago, right? That the value is 5, you said. Okay, let's erase 2 slots. Okay. Now tell me, I have 2 missing value here.
So df now equal to?
No, the df still 1, but this is beyond the df. Right? F is
Okay.
1. Remember, you have a statistic, you can only fill in 1 in this case. If it is a table, okay, 2 dimension, df is n minus 1 multiplied by number of column minus 1 multiplied by number of row minus 1. But if only one array, the df is n minus 1. Okay. So here is beyond the df, isn't it? So now my question, I know the sum is 15. What is the numbers here? Okay, let's forget about the average. let's forget about the others to make it easier for you. I know the sum is 15. Okay. What is the numbers there? Or let's give a name. Okay. Let's give a name. Let's give a name. This is A. Yeah. This is B. Oh, what happened? This is C. This is D. And this is E. Okay. So what is the value of D? What is the value of E? Anyone? Anyone?
I try.
Okay.
So 15 minus by 3 minus by 4 minus by 1. And you got 7.
Have one.
Then you divide to 2 columns.
Yes. So what is D and what is E?
4 and 3.
4 and 3. Okay, this is Darin answer. Okay. Who else want to try? Who else want to try? What is
When you like you
Yes, yes.
minus by 8 and then divide by 2. Is that possible?
what?
So 15 minus by 8, 8 I mean my 15 minus 3 minus 4 minus 1 is like 15 minus 8, right?
Yeah, 15 minus 8.
So it's 7 divided by 2. So D and E is 3.5.
Okay, so D equal to 3.5 and E is equal 3.5. Whose answer is this?
Newton.
Okay. So, Abel, what is your answer? Is it the same as Darin or same as Nyoto, or you create your own?
I mean, if it's not one of these two, then I don't
I
know.
don't say it's one of these two or not one of these two. I'm just asking your opinion.
Yeah, I guess I guess we want to have something divisible by 7, but not the same as the others.
Okay, so what is your answer?
Yeah, I guess 5 and 2. Then.
5 and 2. Is that correct, or you want 2 and 5?
What?
D is 5 and E is 2, or D is 2 and E is 5, like that?
It's fine.
It's fine, this one. Okay.
Yeah.
So Lilian, what do you think? What is D and what is E? Is Lilian here?
I'm sorry, sir.
Yeah.
My internet is really bad.
Okay. So, what do you think? What is your answer?
Oh, I'm sorry, what?
What is your answer? D and E. What is your opinion?
Uh, 5 and 3?
5 and 3? Oh, the sum is not 15.
Hey, wait, what? Oh, sorry, what that? Sorry. 9, 12, 12 and a half. 2.5
2.5 and
and wait, 5, 8, 8.5. Wait, E supposed to be 15 or
the total is 15. The total must be 15. The sum is 15, right?
then 6.5.
6.5. You want 6.5. And then what is D and what is E?
Yeah, E is 6.5, right?
E is
6.5.
5.5. And then what is D?
2.5.
2.5.
Wait, what?
And what is E? From where you get these numbers? What is T and what is E?
Wait.
Okay, okay.
So supposed to be 4.5. Is it? Is it?
Yeah.
Is it four
Yeah, I
and
think
a
it's
half?
4.5, right?
What is 4.5?
The E.
The E is 4.5. Okay.
Oh no. 3.5, right?
Huh?
Hey,
4.
4. Huh? How come it's 4? The total then is 15, right? So 15.
4.5.
4.
Yeah.
Oh yeah. 4.5. Yeah, 7.
Yeah.
The total 7.
Yeah,
Okay,
but
4.5.
okay, so my question to you, okay, why you have a different answer? What is your basis? Lillian, all of you are correct, okay? I'm not saying wrong, okay? Everyone is correct in this case. The question is why? Why Abel created 5 and 7? What is the basis of 5 and 7? Why Darren have 4 and 3? What is the basis of 4 and 3? And Lillian, you have strange number 2.5 and 4.5. What is the basis of these numbers? And Yoto, what is your basis that this is 3.5 and 3.5?
Are they equal to 7 or equal to 15? All of them equal to 15.
Yeah. So if you ask me, I will answer equal to Nyoto. Right? Look, even though your numbers are correct, but you don't have basis, at least Nyoto have certain basis. Why? Well, you don't know, then you assume something. What is the assumption? Equal probability. Right? So then you said, look, I put 4 and 3. So what is your basis? No basis at all. Okay, unless you have certain observation. But if you don't, then you can put any numbers. Everyone can fill in any numbers. Okay, but the problem is there is no known information that help you to assume that way. Correct? So if you don't know, then you need to assume something. But the assumption should have certain basis. Right? You don't argue on certain things without certain basis. So the basis here is equal probability. Okay. Why equal probability? This is the most important part. Why equal probability if your certain basis? Okay. So let me clear these drawings. So suppose you have a half-half. Okay? You have a coins that you put toss. If you get head, you get probability of half. If you get tail, you get probability of another half, right? So then in here I put probability, okay, of 0 and 1. Okay. In the vertical axis, I will have what is called certainty. Okay. Certainty. And of course, in here is uncertainty, right? Uncertainty. Okay. So then I draw this curve. Okay, so this one is about half. So what is this? Here is called maximum doubt. Okay, what is this? This is maximum uncertainty. Okay. So when you have probability of 0, for example, tomorrow the sun will rise from the west or from the south. That probability is 0. Tomorrow, probability is 1 that the sun will rise from the east. So 0 and 1 are actually representing certainty, right? So somewhere in between 0 and 1, okay, there are uncertainty. And the worst case is actually, if you have a coin, okay, the worst case is actually half. When you have a unit, if you have a dice, the probability is 1/6 for each face, right? That means uniform distribution. So in that case, 1/6 is the worst. So maximum doubt happen, okay, when you have uniform distribution. Okay? Maximum doubt happen when you have uniform distribution. So this is the most uncertain things. So when you make assumption, okay, then you assume uniform distribution because you are the most uncertain. This is the basis why, okay, earlier in that filling the array, why you should assume uniform distribution because you are not sure. If you are not sure, then you want to maximize your doubt. Do you get what I'm talking or you don't?
So if we're unsure, we want to maximize doubt.
Correct. So if you are sure you want to maximize your doubt, right? Yes. So in that case, how do? You use uniform distribution. This is the most common sense, right? So your answer earlier, okay, oh, what is that? 2.5, 4.5, okay, 3 and 4. There's no basis. Okay, but you use uniform distribution, there's a basis there. What is the basis? I want to maximize my uncertainty. Clear? Okay. So the question is, okay, I know the principle. Okay, I know the principle that I want to maximize my uncertainty. Okay, actually uncertainty is measured by what is called entropy. Okay, so entropy is a measure of uncertainty, right? So in that case, if I want to maximize my uncertainty, then I maximize my entropy. So this is where the idea of maximum entropy comes from. You get it? Do you get the idea?
Yep.
Yep. Okay. Explain to me what you just learned, so that I will. Explain to me.
We can use maximum entropy to find maximum certainty.
Uncertainty.
A certainty, yeah.
Uncertainty. Okay?
Uncertainty, yeah.
Yes, not certainty. It's the other way around.
Okay.
Okay. So now with that background, so I hope you understand when I start to explain something in the slide. Okay. So let me explain now. Okay. So this is the formal. Cool. Can you see the slide? Maximum entropy method is called
Yes.
MEM, okay, maximum entropy. So I will explain the principle, I will explain the method, and then I will show you in Excel, and finally we will talk about solving queuing problem using maximum entropy. Okay. Of course, if we have time, we can explore certain other things. Okay. So maximum entropy was started by this guy named James, okay, Edwin Thompson James. So you can download his book, Probability Theory. So maximum entropy initiated in 1957. Okay, again, it started in physics. James was a physicist. So what is this? If you have a prior distribution, okay, that satisfy, and you want to satisfy certain constraint, then you want to get what is called posterior distribution. So when we talk prior, posterior, you remember certain things. What is that? Bayesian. Okay. Okay. Do you know Bayes theorem? Did you learn in statistics Bayes theorem? When
Yes.
I think
Yes,
I've
we
heard of
did.
it. I think, yeah.
yes, okay, then it's fine. Okay, so we use what is called Bayesian inference. Okay, so basically when you have the prior and the likelihood, you want to get what is called posterior. Okay, so maximum entropy is a statistical method to determine the distribution of a maximum logical uncertainty. You see this, a maximum logical uncertainty. They want to get uncertainty, maximum uncertainty logically, okay, about certain parameter. What is parameter is up to you. It's very general method. Okay. The most important here is this must be the most consistent with certain amount of information that you have. So if you don't know, okay, then don't assume anything else. Just assume maximum entropy, then you are safe. Okay, so the result of maximum entropy is probability distribution. Okay, so if you think about it, then you say, oh, I can solve this, I can solve that. But be careful, the solution of maximum entropy is actually probability distribution. What is this? This is a special probability distribution which best represent the current state of the knowledge or the information, okay, based on the largest entropy. Okay, and in the context that you have certain prior data, certain prior knowledge. So this is exactly Bayesian inference. So what is maximum entropy principle? Okay, we model all that is known and assume nothing that is unknown. So you only model of something that you know. If you don't know, don't assume anything. So this is the most consistent, isn't it? Meaning, if you have a fact, use that fact. Okay. Otherwise, assume nothing. What is the meaning of assume nothing? Actually, you assume as uniform distribution. Remember why we must assume uniform distribution. Why assuming uniform distribution is equal to assume nothing. about unknown because uniform distribution represent the maximum doubt. Remember that earlier. Okay, so now in absence of any other knowledge, the maximum entropy will prefer the posterior model. Okay, P, Y, X here, X is the data, Y is the output. So P, Y, X here represent the posterior that allocate its probability as evenly as possible. So maximum entropy method is a general purpose method making prediction for making prediction from incomplete information. If you don't have complete information, you can still do because of the maximum entropy. So this is very good method. Okay, actually very excellent. And you use to systematically construct the model, okay, that satisfy this principle, maximum entropy principle, under certain constraint of what you have from the data. If you don't have data, fine, you can assume uniform distribution. If you have data, then use that data. Okay, the rest you assume uniform distribution. Is it clear? So, okay, let me give example a while ago. So here, I have 4 slots, right? The slot represent probability. Okay. Now I have data already. What is the data? The 3, probability of 0.1, 5% and 25%. So what is the last? What is the last slot with the question mark?
So 1 minus 0.1 minus 0.05 minus 0.25.
Correct. And right. So then you get 0.6, right? Okay. So this is what we discussed about earlier. You have a degree of freedom 1, so easily you can fill in. There is no missing information, right? Because degree of freedom is 1 in this case. How about this? Earlier. So now I have only 3 numbers. Here, what is the missing values?
So 1 minus by 0.1 minus by 0.05 minus by 0.25. And you got 0.6 and divide by 2. So
Okay.
0.3.
0.3. Okay. So again, you can fill in with any numbers. Okay. The one that you filled in a while ago was correct, but the most there is no basis if you fill in with any numbers. Okay. The most probable value to solve this problem without any other assumption is 0.3, right? Because you said, okay, this is the maximum doubt. Okay. Next, how about if you have 3 like this?
0.2.
From where you get it?
It's like 0.6 divided by 3. So 1 minus 0.4, 0.6 equals to 0.6 divided by 3.
Very good, very good. So 0.2, huh? Okay, this is another example. So suppose you have y is equal to a, b, c, d, and e. Okay, so say you label the output variables. And then we collect many data with the input x that contain the output variable y. Okay, this is look like very complicated, but look at the result. I want to compute probability of y given x, meaning given the value of x. The constraint is, okay, the y is either A, B, C, and D, and E, right? The constraint is, of course, the total probability is equal to 1, right? So, look, there are many possible combinations that satisfy this constraint. For example, if I put PA given X is 100%, the rest are 0, this is also correct, right? If I put the PA given X and PB given X equal to 90%, the rest is 10%, PE is 0, then this is also correct, right? But again, all these probabilities are not based on fact, okay? They are just based on something that you think in your opinion, and other people will start to argue about it, right? Now, suppose this is your data. So you know that probability of E given X is 40%. Okay? Then you know, if I know this data, then you have a constraint, right? What is the constraint? The probability of A given X, B given X, C given X, and D given X is now become 1 minus 40%, it is 60%, correct? Okay? Then again, that 60% have so many combinations. Yeah? For example, this combination is PA is 60%, the rest are 0, or A is 50%, B is 10%, C and D are 0, and so on. Again, what is the best assumption, okay, that we actually assume nothing? Because all of these numbers represent certain assumption that we assume not based on the fact, not based on observation. Then we can use maximum entropy, right? So in that case, you sum all of them with this 60% divided by how many slots? With this 4 slots, then you have 15%. Okay? Now suppose, again, if you know, okay, the fact, the data represent, oh, B and B plus C is 40%. Okay? Again, you still have many combinations, but if you use maximum entropy, then you can get the value B and C with this 20%, and then you can get the value of A and D with this 10%. Do you get the meaning of this example? The meaning is, if you have certain data, then the rest is constrained. Okay? The more data that you have, the more constraint that you have, the easier you can solve. Okay, again. Suppose you have 5 slots. Okay, the total is known to be 150. Okay, the name of slot is A, B, C, D, E. Without any additional information, what are the value of A, B, C, D, and E? Oh.
So 150 divided by 5.
It is?
30.
Oh, very good, Darin. You are excellent now. Right. So again, you can put any numbers to satisfy that constraint, but the problem with any numbers is you implicitly assume additional information, right? So this implicit assumption is set without any basis. So if you use the most common sense, then you assume them to be equal, right? So in other words, we assume all variables to be uniform probability distribution, which is 1/5. Okay, 1/5 times 150 become 30. What is the basis of the last assumption? The basis is maximum entropy. Okay, so earlier, before James in 1956, okay, Laplace in 18th centuries, 19th centuries, Bernoulli already stated the same principles, okay, or criterion, they call it. Hey, you learned the decision making earlier this semester, isn't it? You remember you use Laplace criterion, isn't it? The principle
Yeah.
of sufficiency. You remember this, right? In decision under uncertainty. Do you remember? Now you can still see the connection between the earlier context of decision making and this one. Okay, so uniform distribution is the most uncertain. Okay, the simplest assumption that is consistent with the data and the problem. So this has been known for many centuries. Okay, under various different names. Okay. They call it Bernoulli principle, insufficient reason, Laplace criterion, principle insufficient. So you can check in Wikipedia or in Google all these terminologies, okay, uninformative prior and so on. So then basically they are all the same. Okay? Assume uniform distribution. Clear? So now, why we, after all those things, okay, they are only principles, isn't it? But why maximum entropy is the best? Because this principle can be put into algorithm. This is the difference. Okay. Earlier we have only, okay, I assume probability distribution is the same, but how you will solve the problem? We need algorithm, right? We cannot do it. But using maximum entropy principles, we can solve using certain algorithm. Okay, when we solve the problem at hand based on the most reasonable assumption that they are equal, we are actually use what is called maximum entropy principle. Okay, what is maximum entropy principle? The probability distribution, which best represents the current state of knowledge, is one with the largest entropy. Okay, as simply as that. Okay, of course, with the maximum entropy with subject to constraint of the prior data. Okay, using this, we can solve using computer. Okay, okay, let's do it in Excel. Open your Excel now. I will stop sharing this one and I will share my screen. Let's practice, okay? I will open Excel. Can you see my Excel? So I will name it A, B, C, D, E. Can you see it?
Yes, sir.
Okay. So I will put some here. I will put the average here. Okay. So let's say we use exactly the same thing. Okay, that we do earlier. What is the number of A that you want?
Randomly, like for random.
Yeah, you can put any number, say integer.
0.00
No, put numbers, integer.
integer.
5, okay. I put 8 here. I put
9.
4 here, and I put 9 here. Okay, so I get the sum, right? So I get the sum, and I get the average. Okay, average there. Okay, so the average is 5.6. Okay, then again the same thing. Okay, so what will happen if I put here 28, okay, and this is 5.6. I will make it remember, and then I delete this, right? And then I said, okay, what is the number of E? So that, right, what is the number of E so that the sum will become 28? Then you said, okay, this one must be 28 minus 19. Oh, that one is not correct because now become a circular reference, right? So Then I will say, okay, I will put 19 here. Okay, then I put the number is 9, I get 28. Okay, if I don't know two of them, okay, then you say this must be 8.5 and 8.5, isn't it? Oh, sorry, 7.5? Oh, 28 minus 19 is 9, so 4.5. 4.5. 28 sorry, when I delete this become 15 now. 15, not 19. 15. So 13, 6.5, yeah? Right?
Yes.
Yes, so this is the one that you said we need to find. Okay, so if we do manually, now I want to do it with algorithm. Okay, I want to get this 60.5 eventually. How I will ask the computer get me 6.5, okay, without I'm doing it manually.
13 divided by 2.
Yeah, but I want to make it, you know, so that I will change this number in yellow. I will get exactly what I want. So
So sum B until F. Oh, wait, I don't know.
okay, so one way is to compute the probability first, huh? Okay, so I compute the probability with this 5 divided by that one, right? Correct? So, okay, let's make it G3 as anchor so that we can put this as probability. And of course, the sum of probability is equal to 1, right? Right? So you don't know this, okay? Next, I want to compute the entropy bar, okay? So, you know the value of entropy? So then we can calculate the entropy here. So entropy part is equal to minus of the probability multiplied by ln of the probability, right? But there is a problem. What is the problem? Oh, if probability 0 is not okay, then we say, okay, the entropy part, if the probability is 0, then make it 0. Otherwise, compute that entropy part. Okay. Okay. Then what is entropy? Entropy is the sum of that. Entropy part. Clear? So I get the entropy already. Okay. So I want to solve it using sulfur. Oh, do I have sulfur here? Do I have sulfur here? Wait, sulfur must be here, but not here. Good. I don't have sulfur. So then I go to File, Option, Add-ins. Okay, in Add-ins. And then when Add-ins open, we can go here. And there is sulfur there, sulfur Add-ins. Okay. When the solver is open, you see the menu solver is here. This is Excel solver. Okay. Then I say, okay, I will name this. I name this entropy. Entropy. Okay. And this is something that I want to know, right? Okay, so I use solver. Maximum the entropy by changing what? By changing these two variables, okay? Subject to constraint, what is the constraint? Now you add the constraint, okay? The constraint is the sum must be equal to 28, right? The sum must be equal to 28. So I click OK here, and I just solve it. Solve. Oh, solver found the solution. What is the solution? Then I got 6.5. See? Can you see it now?
Yeah.
Yes. So using maximum entropy, okay, I just show to you that there's an algorithm. Okay, solver is practically search algorithm, optimization algorithm, right? So then you maximize the entropy, okay, subject to certain constant that you want, then you get 6.5. Nice. Can you do it? Can you do it? Okay. Show me your screen so that I know are you doing it well or not. If you have problem, then I will help you.
Oh, wait, I'm using my phone. Wait.
Can you share your screen?
Wait. I haven't done it, sir.
Haven't done it. Okay. Lillian, can you share your screen?
Okay, wait. So the yellow one is the given, right?
The yellow one is the given, correct?
And then this is what we must look for.
Yeah, this is what you will look for. The algorithm will fill in that one.
Okay, so now I have to fill the probability.
Correct. So probably the probability you can put in.
Okay, so the probability, should I, wait, how do I get the probability?
P3 divided by G3.
Okay.
That one. It's easier if you put in the same column so that you will not make it difficulty
Okay.
to understand. Right. And then G3 must have certain, no, it will not become correct. You know why? Because G3, you put a dollar sign there.
Yeah.
Okay. Then you can copy. Make sure that this is correct. So check the sum is equal to 1. Yes. Okay, now you calculate the entropy part. Okay, this is the entropy. So how do you calculate the entropy? Equal of the probability multiplied by ln logarithm. Log.
Oh.
Either log or ln. Okay, ln.
Oh, so okay, wait.
That one is okay. Log, if you want to use ln, is okay.
Okay.
Ln
Ln of
probability. No.
ln of probability.
Correct. Yes, close it, but negative, right? So you put negative.
Oh, like
Yes.
I must make
Negative.
absolute
No,
or
negative.
just negative.
Negative.
Okay.
Okay. So, and then when you copy all until F, there's a problem, right? Okay, then you, to solve that problem, okay, in B, come back to B6, B7. So you put if. In the beginning, you put if in the beginning, yes. If the probability is less than or equal to 0, no, when B6, if the B6, if B6 is less than 0 or equal
Or less than or equal
equal
than
0,
0.
10, 0, 0, right? Comma, negative B6. Yes, and then close the parenthesis at the end.
Oh, without the ln?
That one, the loan is already there. So,
Oh, okay. So like that.
yes. Then copy. Right, then you sum. You can copy the sum anyway. Yes, that one is the entropy. Okay, so you name it entropy. G7 is the entropy. You know how to name in the box. Yes, you name it entropy. Yeah, without H actually. Anyway. Okay, so then you solve for now. In data, do you have solver? Oh, you have. You do have solver.
Yes.
Good. So then maximum the entropy, objective value is the entropy.
This one?
Yes, that G7, yes, maximum. In variables is the one that you put as orange. The two of them, yes. Subject to constraint at sum is equal to the sum G3. You point to G, okay, equal to, seems to equal 28, right?
Okay.
Click OK. Then solve. Oh, you got the solution. Is it true? Click OK.
Yes.
It's 6.5. Okay. So is it clear now? How about the others?
I still have problems.
Okay, so, show your screen then.
Okay. This one.
Okay. So entropy part. Right. This is V5 is no, why you put negative? If P5, not negative P5. Yes. Enter. And then copy to until F. Yes, and then you sum. Sum of all of that. Okay. Okay, name it entropy. Yes, that one. Okay, you already named it. Good. Then you solve using solver. Do you have solver? In data, no, you don't. Go to file. Okay, more option. Add-ins. Click. Go. Go. And then solver. Okay, click OK. Wait for a little while. There you have solver. It will solver. So what is your entropy there? Can you go? Set objective is your entropy. Where is your entropy? There in
G6.
Yes, G6. You maximize changing the value of, yeah, that is already maximized. Changing the value of variable cell. You go to E3 and F3. You just click that arrow. Yes, and then, no, not that one. The E and F3. E3 and F3. That one, correct. So you put that. And then subject to constraint, add. Subject to constraint, add, you add. Okay, the sum with this G3, go to G3, yes, equal. Okay, what is your 28? So you put, you can point to one cell, you can type a number, 28, for example.
This one.
28, just 28.
8.
Yes. And
But my sum is 24.
oh, 24, okay. Then you point to that G1, so that constraint is
G1.
G1. Okay, point to that one. Okay, your sum is 24. Then okay.
Then I
No, not click OK. Solve. Solve. Click OK. Click OK. There you get the value. Okay, so 3.5 and 3.5. Of course, it's numerical, so not exactly 3.5, but it's close, right?
Mm-hmm.
So you
Yeah.
okay, very good.
Okay, thank you.
Thank you, yeah. So
Sir,
yes,
I wanna
Eugene, you please
I want to ask.
show your screen
Uh,
if you want to.
no, actually, it's more like about the concept. Like when I saw when I tried to do this, then I also saw Lilian and Darren's screen. Solver can only give the two same exact solution. So that means they cannot give like a more variant solution. I mean, like
can. I will show you in that case. Okay, I will show you in a while. Okay, in my screen. I will show
okay.
you my screen then. Okay, so let's try another way. Okay, suppose now we have instead of this value. Okay, first, can you see my screen already? My Excel.
Yes, sir.
Okay, so then I change this. Okay, I change this into look. I want to get the average is not 5.6. I want to get the average is 6. Is it possible? Okay, let's do it. Okay, so I go to the data solver. Okay, that constraint I changed. Okay, that constraint now I want to get that average here must be equal to, I want to get it 6. Okay, I want to get it as 6. So where is this? This is I delete. Okay, so look, now instead of using the sum, I'm using the average. Okay, look, now the probability distribution is no longer equal. You see that? Oh, still equal, 7.5. Right, 7.5. But the result is different. Okay, because the sum is no longer 28. Now the sum is 30. Correct? How about this? If I don't want this to be 2. Okay, I also don't know this. You said, oh, it's only 2 numbers. No, I want to have 3 numbers. So in that case, I change this into a different color so that I know that this is the one that I want to know. Okay. Okay, so then I do it again in Excel using solver. I want to maximize the entropy subject to changing of the cell. What is the changing of the cell? This one, the 3, right? This is the one that I want to know. So changing of the cell. Again, subject to constraint that the average is still 6. What will happen? Oh, I got the sum still 30, and then they are equal, right? Okay, then you said, oh, I don't like the sum is 30. Apparently, based on my data, the sum is actually 35. Okay, then you add the constraint, okay, that the sum is actually 35. Okay, and then I solve it. Oh, that data must be wrong. Why? Okay, maximum entropy tell you that it is not possible to have a average of 6 with that data, and okay, that constraint is not correct. See, maximum entropy will tell you that if your data, certain of your data is probably not correct, it is impossible to have a constraint these 2. Either the sum is 6 or the sum is okay, maybe not correct. Maybe this is not 7, not 6, maybe 7. Okay, so okay, if 7 is correct, so this is the value. See, now the sum is exactly like my constraint. Okay, the average is again the same exactly like my constraint, but I can get 3 values here. And look at the probability distribution, still the same. Okay, so do I answer your question, Eugene?
Yep, finally. Okay, thank you, sir.
Okay, okay. So, is it clear? Okay, now try. Okay, share your screen. I want you to create the constraint that the standard deviation is actually 10. The constraint is standard deviation is 10. Okay, you have 2 numbers given based on your data and 3 numbers missing, right? But you know, you don't know the sum, you don't know the average, but you know the standard deviation. Standard deviation is 10. Can you solve it? Anyone can solve? Show your screen. Okay. So, using maximum entropy, you can solve any missing values problem. Right? This is like an inverse problem, actually. You know the answer with this standard deviation, and you know certain data, okay? And you don't know some part of the data. Okay, if you know the output, you don't know the input, then use optimization. It is in this case maximum entropy. Then maximum entropy will solve it for you. Nice, right? Very powerful. Okay, give me the solution that standard deviation is 10. Abel, Nyoto.
Using Excel. Okay.
Yes. Show your screen. Oh, you didn't do it. Okay. I need to check one by one. Come on.
Which one? I do the one that you do before, like the sum is 28.
Up to you. Yeah. But now not. I want the standard deviation is 10. Say you have two numbers, you can fill in any numbers. 5, 7, or 9, whatever numbers. Okay, and
Okay.
three of them are empty. So just mark them that is different colors. That you put them as color. D, E, F, you put them as color. Okay, that one. So that you know this is the one that you want to find out. Okay.
Okay.
Calculate the standard deviation in 8.
Here.
Yeah, standard deviation STDF. ST equal ST equal ST S standard deviation ST. And that one standard deviation. Standard deviation of population. That one STDEF P. Correct. Okay. Click. Okay, of all of them until F. Yeah. Okay. Close it. Okay. This is 1.5. Okay, I want it to be 10. What
Using solver?
E and F? Yes, using solver.
No.
Yes, using solver.
Solver. Where is
your solver? Oh, you don't have solver, so how do you get your solver?
what? Wait. Why don't I have solver? Oh, it's still new.
Options. Cut-ins. Yes, go. Solver. Okay. Okay, now solve it. Oh, your license is not genuine.
Yes, I find it cheap. So the objective is here.
No, the objective is maximum entropy. How do you get that? If you, okay, try it on your own so that we will see. Right, you don't know, right? So then you calculate the probability and you calculate the entropy first.
Oh, this one.
Divided by sum. You did not make sum yet. So in G, you calculate the sum. Sum until F. Okay. And the sum of P divided by G. Okay. And then you put, you press enter first and then F2, you put the, and then you copy. Okay, make sure the sum probability is 1. Just to make sure. Then you
So
can
this one.
entropy. Okay.
I got confused after this.
Okay,
After
that's why you try. Okay, you try so that you will know. If you have a problem, I will help you. So go. Entropy, what is the formula of entropy? P ln P, right? Sum of minus P ln P, okay, equal to probability P4 multiplied by equal multiplied by ln ln
Okay.
ln, yes, and then parentheses of the probability. Yes, close it. So it's negative, so we put negative there. After the equal, you put negative. Okay. Then if you copy, it will have a problem.
Like this?
Yes, go continue until F, right?
Okay.
A problem, right? So how to solve this problem? This happened because your probability is 0. So come back to P5. Come back to
P.
P5. P5.
P5 here.
Yes, and then you put if after equal. If, yeah, you type if parenthesis, no, if parenthesis P4 equal less than or equal to 0. No, P4, you type P4.
This is the, so still minus. So
Yeah, that
this
one's
one,
comma. You just put comma. P4
P4.
less than or equal. No, P4 less than equal 0, comma 0, comma. Okay, and then go to the end and put close the parenthesis. Right, and then you copy.
Okay.
G5, you sum. Just sum of the entropy part. Close it, and then name it G5 as entropy. Okay, we got that. So then you solve for now.
So far.
Okay, so go to G5, it is the entropy. No. Objective function is
Entropy.
set objective. The objective is entropy. Which is, well, where is the entropy?
This one.
G5, correct. Okay, and then changing variable. Where's your variable that you want to change? The one in green. No, not that one. Yes. Correct. And constraint. What is your constraint? No, it is not.
What? Where is it?
H2. H2. Cell reference is H2 equal. No.
Wait. I cannot.
You can.
Wait. I cannot click the. Okay.
I cannot
Wait.
see. I cannot see your screen.
Yeah, it got an error. Can you see it now?
Okay.
This one is
Yes,
this one, right?
correct. And then equal.
Equal.
10. You just 10. Okay, click OK. And then solve.
Okay, so
So cannot find visible solution. Oh, why? Maybe too big. Okay.
So
See your solver again. Changing of T2 to F, correct. Maximum entropy and H2 is 10 is not possible. So change that to say that one change. Say for example 1. There, you got the answer. Okay. So click OK. Now you see here, when you said standard deviation as your constraint. Now look at the probability distribution. They are not the same. Probability of D, E, and F are not the same. Can you see that?
Yes.
Okay, so remember, even if you use the maximum entropy, the result is not always equal probability, depending on your constraint. Okay.
So the one with the equal probability, we using which constraint, sir?
If you use sum, if you use average, you probably will get
Equal probability.
okay. Nice, right? So the algorithm solve it for you. Can you see it? Okay. Then you can add more constraint if you want. The standard deviation is like this, the sum is like that, so you can add.
The sum of the probability or the entropy?
No, the constraint. Add constraint. So the key in optimization is in the constraint. Objective is always entropy in this case.
Okay, so we're looking for the entropy.
Yes.
So we can use this.
What?
The constraint, the
It's
sum
up
of.
to you. Say, for example, the sum. You can add the sum is 35. Say G2, you know, G2 is equal to 35, for example. Click OK. No? Click OK. Okay. Solve it.
Oh, too large.
Cannot find. Yes. Cannot find mean your constraint is too restrictive. Okay. So probably 35 will not be feasible. So you can change that to 30 probably. There.
Still cannot find visible.
Still cannot find. So you can, okay, this is the one. Put 0 in the beginning, in the green, so before close the solver first. Okay, and put 0, 0, 0. Okay, then solve again. And solve. Still cannot find. Okay, so in that case, you need to change the constraint. What is the meaning of this? Meaning it's too restrictive. If your constraint comes from the data, so there is probably some error in your data.
But we got equal probability.
Yes, in this case, because you constrain sum, then you get equal probability. But the standard deviation is too restrictive. Maybe, yeah, we probably need to put it 0.5 or 0.7.
0.5?
Okay, click OK. Still cannot find. So if you have two constraints, okay, it's difficult to, initial value sometimes matter, so you can reset.
Nope.
Okay, this is the problem. You know what? Okay, try again. In solver, if you allow negative value, so make unconstrained variable non-negative, that one you uncheck, yes. Then you solve it. Put it from 0, initial value is 0. Okay, solve it again. Still cannot. Okay, your value is too restrictive in that case.
So the value here is too restrictive.
Yes, the constraint. One of the constraints is too restrictive.
So if I try to delete this, then
yes, if one of them you delete, of course you can. Your apparently your restriction is the problem with your constraint is not in the sum but in the standard deviation.
SD, yeah. So if if we use the sum, we can probably still get the answer.
Yes. So you can change your constraint. Remember, so the algorithm help you to realize something inside your data. Okay. Yes, of course you can.
Oh yeah, 30 is already there. Yeah.
Yes. And of course, if you sum the probability distribution is equal.
Mhm.
Yes.
What does it mean with the probability equal using sum?
Meaning that maximum entropy automatically assign uniform probability distribution values.
So it's like when we use when I said like 0.6 divided by 3.
Correct, correct.
Then the 0.2, all of them got 0.2, so the probability is all equal.
Yes.
Okay.
Okay, so the algorithm solve it for you, right?
Mm-hmm.
Here you do it manually.
Yes.
Yes. Now you can use computer, but when you use computer, that means now the technique will automate your problem and can be generic solving any problem, not just the one that you manually inputted.
Mm-hmm.
So it become very powerful.
So if we have we want to fill up some empty fields with the
Yes.
known sum, then we can find the probability, then find the entropy, then you solver to use
Correct.
maximum entropy.
Correct. Okay, clear?
Okay.
Is it clear? Okay, so let's rest for 5 minutes, and then now is 10:28.
Yes.
Okay, and when we come back, we will continue again. Yeah? Okay, let's continue. I will share my screen again. So the simplest maximum entropy formulation is this. You see? So I'm just using this is the one that you just did, okay? But we formulated into mathematics, okay? So that you will know how we will write. So what do you maximize? We find the PI, it is the probability, right? To maximize this minus sigma P ln P, right? PI ln PI. What is this? This is the entropy, right? Okay, subject to constraint what? Subject to constraint, of course, the maximum probability is equal to 1, right? So, okay, so if you solve this, you can solve this mathematically, you can solve this using Excel, but if you solve this mathematically, this is how you will do, okay? So you use what is called Lagrangian function, L. That means you put the constraint, and then first you put the objective function, and then plus lambda times the constraint. Okay, the constraint you put them into equation, and then you set that Lagrangian function derivation to first derivation equal to 0. Okay, first derivation by its probability and by lambda. Okay. So it will produce, if you compute, it will produce P equal to 1 over n. So with this uniform distribution. Okay, so why you use optimization? Okay, Why should we make a simple complex problem earlier just to find simple things, missing value that you can put manually, okay, into complex formula of maximum entropy. Okay? Again, because maximum entropy translates the principle into algorithm, right? You have seen the power. Okay? Using maximum entropy, you can solve the problem at hand into constraint optimization and finally solve it numerically using computer, right? So once you can solve, you translate your problem into algorithm, okay, then of course you can do automation. Okay, this is the motivation why you learn maximum entropy. Okay, this is the one that you have done earlier. Okay, so look at this. Say you have 5 slot, total 150, right? And you know that A is equal 5, B is equal 25. What is the value of C, D, and E? You solved this already. Now, I want you to put into a maximum entropy formulation, okay? Formally. So, what you know? What you know is A equal to 5, B equal 25. So something that you know, you will put them into probability, okay? P1 is 5 over 150. P2 is 25 over 150, okay? And you know the sum is 1, sum probability is 1. So this is the optimization formula of maximum entropy, subject to that 2 constraint of the data. Is it clear? Can you write the optimization formula, something like this? And if you know this formula, can you solve it using Excel? Yes or no?
We can.
Okay, if you can, then try this and share your screen.
Oh, I'm just like, well, that's a wrong move.
Okay, okay, solve this using solver. Come on, I give you the optimization and solve this using Excel. Come on. So, who want to do this in Excel? Yes, Nyoto. Okay. So what we have earlier in the slide, P1 is given with this 5 over 150. So you put P, yeah, that one 5, the other one is 25. And the sum is 150. So the sum is 150.
Sum of 3 of this.
5. No. So actually you already did it. You look at this. The one that you put here in solver is 3, right? So then you go to solver, change this one. C2, you change that to 25. Okay, and then go to solver. Right, that constraint, that 30, you change to 150. Okay, and solve. Then click OK, you get the solution. You see? The result here. The result is 26%, right? So
Yes.
if you want to get that into go home, yes, and click the general there, change, yeah, no, you change it into a fraction.
Ah, okay.
put that again. In that fraction, you change into a more format, yes. And that fraction, you put it into 3-digit. There. So 40 over 150 is 4 divided by 15, right?
Mm-hmm.
That is the answer. Okay.
Okay.
So you see now you go to the slide again, then you get exactly that. Right? Can you see it?
Okay, CDE 40. Yeah.
Yes. So you did it, right?
Hmm.
Hmm.
Mean value of the first slot will be 80.
Yeah, and standard deviation will be 20. What is the value of A, B, C, D, and E? Oh, can you solve this? Anyone? No, again.
Now I start to. Can I try it one more time just to make sure that?
You try it on your own. I want to see someone else.
Okay.
Come on.
Okay.
Come on, guys. Stephen, you did not show. Come on. Stephen, are you still there?
I'm still here, but I'm using my phone, sir.
Come on. Solve it. Did you solve it? Can you share your screen?
Yeah, I can solve it.
The SD is 20, yes, sir. So we don't know the sum. We just know the mean.
You know the mean and you know the standard deviation, right?
Yes.
So you know this. You have 5 slots.
Yes.
You know the mean value is 80, standard deviation 20. What is the value of A, B, C, D, E? Oh. Eugene. Share your screen. How you solve this? Easy, right? Supposed to be. Come on. Eugene, are you still there?
I'm sorry, sir. I'm in the toilet right now. So sorry.
Okay. So Lillian.
Yes.
Okay. Solve that problem. You have 5 cells empty.
Mm-hmm.
The mean is 80 and standard deviation is 20.
Okay, wait.
Okay, share your screen so that we can learn from you. Very good. Yes. So that one is equal to 80 equal.
Okay, wait, sorry.
Okay.
Add.
Yes, the standard deviation is 20. Click OK.
Oh.
Error, you know what's error? Because in the beginning you put it division by 0. So put 111 as the beginning in your that one. And
Also, the starting value can be up to us.
It's up to you. Starting value is up to you. Sometimes starting value will matter so much in optimization. You solve it again. Cannot find feasible solution. Okay. Okay. So now change the value, okay, of the constraint so that you can solve it. Can you?
So I changed the standard deviation.
Yeah, standard deviation you change. 1, for example.
Okay.
1, 1.
For example, 10.
1, yeah, 10. Okay.
Okay, 1.
Cannot find the solution, make it the constraint is non-negative, and check the non-negative. Make unconstrained variable non-negative.
Wait.
That one you uncheck.
Okay.
Okay, this cannot find. So your problem is to find the initial value matter. So you name initial value, put 1, 2, 3, 4, 5, for example. Okay, and then solve it again. This H3 is the sum, is it? Still cannot. So then you sort until you can find. Okay. Oh, it's closed already. So 1 is
Yeah, but the sum is 66.
okay. So probably you increase the standard deviation to 2. Change to 2.
Oh.
Oh, you got right. Okay. Right. So you get the standard deviation exactly 2. Okay, and then the sum is 400. And look at the probability distribution. They are not equal. Okay. Once you use standard deviation as one of your constraints, then the probability distribution is no longer equal. Okay. Nice. So don't say that maximum entropy always create uniform probability distribution. Not always, yeah, depending on the constraint that you set. Clear, yeah?
Yes.
If you don't have constraint of standard deviation, yes, it will make it equal. Say your constraint is sum or mean, it will become equal. But once you create very complicated constraint, it's not necessarily equal. Okay, this is one of the argument. Oh, always equal, not necessarily. Okay. Okay. I'll go to the next topic, which is queuing theory. And we will solve this using maximum entropy. Okay. So I will share my screen. So I'll give you an example. Okay. That we can combine maximum entropy and queuing theory, the one that we learned last time. Okay. And we can also see how the maximum entropy is actually related to maximum efficiency of the system. Okay. Say, you remember we discussed about generalization of queuing. Okay. Traditional queue we discussed last time is just a waiting line. But when we start to think queuing as a general process, where people, material, and information need to wait, okay, at certain time to get a service, then you start to think queuing as a combination between demand and supply, okay, where the purpose is to transfer the information, material, or people, okay, between the customers and the server. Okay? The customer represents the demand, and the server represents the supply. We have learned this in the last lesson, right? Suppose now you have 1,000 customers arrive at once. Say, suppose you are in a conference, okay? And the service time is 1 minute per customer, and you have only one server. The question is how long the queue will be. Okay, so you have only one server. Okay. you have only one server and this is the customer being served, and the 999 customer are waiting, right? So you have 1,000 customers multiplied by 1 minute per customer, then you will have 1,000 minutes. That means 16 hours and 40 minutes. Are you still there?
Yes, sir.
Yes, sir.
No problem, yeah. So then you remember the queuing rule of thumb that I proposed last time. So remember the N is the number of customer demand. R here is the service time per customer, represent the supply. S is the number of server, and T is the total time to finish the queue, okay? Represent the delay of the system performance, okay? So let's use that, okay? So suppose you have 1,000 customers and the service time still the same, which is 1 minute per customer, and you have 100 server. The question is how long the queue will be?
10 minutes.
How do you get the 10 minutes?
1,000 customers divided by 100 server. Then you divide again with 1 minute per customer.
Yes. Okay, so the queue length will be 10 customers, right? Per server, correct? So 10 customer per server multiplied by 1 minute per customer in the server, then you have 10 minutes. From 16 hours, okay, now if you have 100 server, it becomes 10 minutes. Imagine from 16 hours now become 10 minutes, but you need 100 server, right? Okay, so this is the derivation of queuing rule of thumb last time we discussed about. Okay, so wait a minute, I divide by 100 here, right? You have 1,000 customers and then you have 100 servers. So you divide by 100, right? 1,000 divided by 100, right? That's why you get 10 minutes. So there is a hidden assumption when you divide, actually, right? What? In any division, the distribution must be uniform, isn't it? So we distribute the customer equally among all the servers. Okay. Now, I will show, okay, that the uniform distribution will produce the most efficient system. Okay. How I will show. So I'll give you very extreme example. Okay. N is 1,000 customer, R is 1 minute per customer, okay, S is 100 server as before. Okay. But now the distribution is no longer uniform. Okay. Say 99 server will serve only one customers and the one server will serve remaining 901 customers. The question is how long the queue will be. How long the queue will be.
The longest one,
What is the longest one?
901 times 1 minute.
Correct, correct. So look at this. I have the same number of server, right? I have the same service time, which is R is 1 minute per customer, right? And I have the same demand, which is 1,000 customers, right? But why now the performance is so bad? It's now 900 minutes, 901 minutes. Why? Earlier it's only 10 minutes, remember?
Because you only have one line.
No, I have 100 line.
Because
Oh.
the server not serve equally.
Correct. Because the server not serve equally, because the distribution is not uniform distribution. Right? So this is to prove to you that uniform distribution is actually the most efficient system, isn't it? If the distribution is not uniform, right, then one of them will be more than the 1000 divided by 100, which is 10, right? That means it will not become efficient. Is that correct?
Yes.
Yes. So this is just to show you, okay? We use exactly the same number of server, but the queue length will last much, much longer when you are not using uniform distribution, right? So okay, how about this? Suppose you're not using uniform distribution, but not extreme, okay? Something like this. Some are 2, some are 3, some are 5, some are 15, and so on. So what is how long is the queue length in this case?
The maximum one.
The maximum number of customers, right? Correct.
Yeah.
Okay. So the delay, okay, will be the largest number of customer on a server, which is of course larger than 10, right? Why? Because some server is less than 10, correct?
Yes.
Yes, yes. Because why? Because this is non-uniform distribution, right? This is to prove, okay, a simple proof that uniform distribution is the most efficient, correct? 10 is the most efficient in this case. Correct or not?
Correct.
Any argument? Okay. So look at this system, okay? You have 100 cast server, 1000 demand, and it is only efficient if you make it as uniform distribution. If non-uniform distribution, especially if you have an extreme, then it will not serve you well. So imagine this server represents the demand and supply, right? The system is represent demand and supply, okay? That means in the society, okay, when the distribution is actually not equal, okay, there is a rich and there is poor, right? Then it's actually is not efficient one. So it's not Pareto optimal, remember, in game theory. Okay. Okay, so this leads to the theorem that uniform distribution of the demand, which is the customer in the system, will make the most efficient utilization of the system. Okay, can you remember this? Okay, so the most efficient utilization will be the minimum of the maximum queuing time, right? So how do you calculate efficiency? In this case, you get the maximum queuing time, okay, and then what is the minimum of that, right? So, and you know that the most efficient utilization happens when the customer is actually distributed equally among all servers. Hi, this is happening because we assume the service time for all servers are equal, right? Now, okay, this is just to prove by contradiction, okay? Assume that uniform distribution is not the most efficient. then the delay is equal to the maximum of the waiting time in the system, and the assumption implies that the delay is greater than the mean of uniform distribution. Then the delay is less than the uniform distribution. However, because it is not uniform distribution, then some value must be larger than the uniform distribution, right? Because some value is also lower than uniform distribution. Then the delay will be larger than the uniform distribution, which is a contradiction. So we prove here, okay, logically that uniform distribution is the most efficient in this system. Now, I have another system here. This is the one that you will do in your homework. Oh, first thing first. You have 30 customers with 3 servers. Let's say the service time is 2 minutes per customer. So what is the delay in this case? Okay, so I will draw, you have 3 servers, okay, each server is 2 minutes per customers, and you have only 30 customers. So you divide that 3, that means 10 customers per server, correct? And then multiply by 2 minutes per customer because they are equal. So maximum delay will be 20 minutes. Is that correct? So let's use this value 20 minutes as your base case scenario. Okay, this is the base case scenario that you will compare with other scenario later on. Okay, is this the best? Is this the best or not? Okay, suppose now this is your homework. Suppose our system have 3 servers. Okay, the average service time of each server is as follows. Server 1 is 1 minute per customer, server 2 is 2 minutes per customer, server 3 is 3 minutes per customers. Okay, the customer arrive once per batch. Okay, so distribute the 30 customer per batch to each server so that the maximum total queuing time will be minimized, and show your computation in spreadsheet. Okay, I will solve this, okay, your homework. So suppose you use equal demand, okay, like earlier. So server 1, 1 minute per customer, server 2, 2 minutes per customer, server 3, 3 minutes per customer. So then you distribute equally. So 30 customer, you distribute equally, that means 10 customer per server, correct?
Correct.
Correct, 10 customer per server. Then the queuing time will be, for server 1, 1 minute per customer, right? So 10 times 1, so 10 minutes. Server 2, right? 10 customers times 2 minutes per customer, then become 20 minutes. Server 3 is 10 customers times 3 minutes per customer, become 30 minutes. Remember, the queuing time for the system is the maximum queuing time, which is the maximum between 10, 20, and 30. Correct? So, using this kind of distribution, equal distribution, now you have maximum queuing time is 30 minutes. Hey, 30 minutes is larger than 20 minutes of our base case. So this is not good. Not good distribution, correct? Okay, so let's try another way. Manually we change, okay? How about like this? Say I have distributed, I'm just trying, okay? So let's try 15, 10, and 5. 15 in server 1. Okay, 10 in server 2, 5 in server 3. Okay, then let's calculate the queuing time. 15 times 1 is 15, 10 times 2 is 20, and then 5 times 3 is 15. The maximum between 15, 20, and 15 is 20. Oh, using this distribution, we are reaching the performance equal to the base case, which is 20 minutes, right? Okay, let's try another scenario. Let's change to 19, 8, and 3. Using this scenario, you will get what? 19, 16, and 9 minutes for server 1, 2, and 3 consecutively. And the maximum queuing time become 19. Wow, it's less than 20 minutes of the base case, which is better, right? My question to you, hey, we have 30 customers. This is the server 1, 2, 3, the service time, 1 minute, 2 minutes, 3 minutes per customer. Can you distribute the number of customers per server so that this is optimum? I get 19 here, it's better than 20. Can we improve this or not? What do you think?
A little bit.
How? What is the...
Two customer at the server 1 to the server 3. And then it will become 17 minutes, 16 minutes, and 15 minutes.
Okay, so I try here 18, 8, and 4, I get 18 minutes, right? And I got here 17, 8, and 5, again I get 17 minutes. So this is much, much better, right? So what is the best? Okay, the best is, what is the best? So look at the way I do this. I'm doing trial and error, right? Right?
So the 17 is less waiting time, right?
Yeah, 17 is less waiting time, correct. But I don't know what is the best, right? So then we can solve this using maximum entropy. So how to solve this using maximum entropy? Do you know?
Solver again? No?
Yes, yeah, okay. Can you make it in solver?
So the objective is the total queue time.
Oh, the object.
The objective entropy. Sorry, objective is
Entropy.
entropy.
Entropy. Okay.
So we can just
The
change the.
probability. Right. So to get entropy, you need probability. Then you want to know what is the probability, right? Oh, so right. There are many possible configuration of demand. Okay, trial error works, but unsystematic. How to solve this optimization? Use maximum entropy. Let's try, okay? Let's try. The question is, what is probability, isn't it? Right? Let's try this. Say, let's try that the total queuing time, okay, as our optimization. What will happen? The total queuing time will be n times r, right? N is the number of distribution per server, r is the service time. Okay. Okay, can you solve this using solver? Use this optimization. Can you solve this using solver?
Maybe.
Yes. Okay. Make it. I will wait.
So basically what I have learned today is that the matter of finding, can you hear me? Can you hear me?
Yes. What?
So I think basically what we have learned today is finding maximum entropy is easier using solver, as long as we can set the constraints, and the constraints is not too complicated, such as the standard deviation, and then to combine the usage of maximum entropy and queuing theory, we need to figure out about the invariant.
Correct. Correct. Okay.
But yeah,
Good.
the thing
Good.
is, I'm still not quite getting how to get the invariant.
The invariant is art,
Okay,
meaning that you need to try.
okay, yes, sir.
Okay. So the more experience you you have in certain areas, then you can guess it.
Okay.
Okay. Yes. The one that I said art mean you need certain experience. If you try a lot of times, then you know.
Okay.
Okay. So there is no way to tell that this is must be. In fact, in research, okay, you don't know what is the invariant that you will use as probability. Then you try this, try that, and so on, and finally you find. Then that is the one that make the result valuable. Okay, finding the invariant is the key.
Yes, it is.
Okay. Okay, good. So I have homework for you, exactly the same as what we just show in the class today. So I hope you can solve it. Okay, using Excel. Can you check in Moodle?
Yeah, the one that, if I'm not mistaken, the due date is like
Next
still
week.
next week, yeah. But it's
Yes.
already started from yesterday.
Yes, no problem. Yeah.
Oh, okay.
Okay, so good. So see you next week then. Please read the, I think the next meeting is ideal flow network, right? There are a lot of material there. Please read before the class.
Okay, thank you, sir.
Okay, thank you.
Okay, thank you,
Thank you,
sir.
sir. Have a good day.
Yeah, you too.
Thank you, sir.
Thank you.